Chapter 16, General Linear Model. In this chapter, we're going to slightly modify the equation, regression equation. We'll replace x sub 1 with z sub 1, x sub 2 with z sub 2, and so on. And that makes this a generalized regression equation. So each of these z's can be just the x's that we saw earlier, or they could be a modification of the x's, like maybe x squared, or maybe 1 over x, or maybe logarithm of x. So some modifications can be performed with the x's, and that is what is represented by the z's instead of x's. Now, why would we do that? Well, we looked at residual analysis for the verification of the assumptions. If some of the assumptions are not validated, then these transformations can mitigate those instances. So let's look at one such modification first, and that is modeling curvilinear relationship. If the points do not follow a straight line but a curved line, then the simple linear regression assumption, the model assumption that y is equal to beta 0 plus beta sub 1 x is not going to hold. So maybe a squared term would correct that problem. So let's look at an example. This is from your textbook. We have a manufacturing company that manufactures industrial scales and laboratory equipment. So the managers, they want to investigate a relationship between the length of employment of the sales representatives and the number of units they sell of the laboratory scales. So they want to predict the sales units with how long the salespeople have been employed in the company. So dependent variable is scales sold, and the independent variable is how many months they have been employed with the company. So if you just use the linear model like what we had done before, you'd see that the model assumption is not valid. So if you include another term and the independent variable is the square of x, then this model may fit the points better than just the linear model. So let's go to Excel and take a look at how to fit this squared term. Okay. So in this example, our dependent variable is sales, and independent variable is the number of months of employment. If you prepare a scatter plot of y with the x sub 1 in the x-axis, since y is on the left side, we have to just include the y first, insert a scatter plot, and then you add the x-axis value by going select data, edit, and in the x series include the x values. And then you have to format this, get rid of this, and add titles. Now if you look at the plot, you see that there is a kind of a curved pattern to the data. It's not like a straight line. A curved line describes the pattern better than a straight line. So we have a second order polynomial model, in other words quadratic, where z sub 1 is just x sub 1, z sub 2 is x sub 1 squared. So we set up another column, and this one is x sub 1 squared. Make that squared superscript. Okay. Then you take the x sub 1 value and square it. That will be our second column of independent variables. Now run the regression model. Regression from data analysis. Okay, data analysis. Select regression. And Y range is that. X range is now x sub 1 and x sub 1 square. Labels. And let's put the output right there. Now let's go ahead and format the output. So that's B sub 0, B sub 1, and B sub 2. So let's now construct the y hat equation. So y hat is 45.35 plus 6.34 x sub 1 minus 0.03 x sub 1 squared. Now let's see how to use this prediction equation to predict sales. So predict sales for the next period by a salesperson who has been with the firm for 22 months. So x sub 1 is 22. So x sub 1 squared is the second x variable. And then our y hat is b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 1 squared. So our forecast for number of scales, laboratory scales that this salesperson with 22 months with the firm is 168. Now let's look at the fit case. Here the R squared for the quadratic equation is 90%. Now if we did just a linear fit, the R squared value is, the Y range, X range is just X sub 1. So this will give us the linear equation. So the R squared improved from 78% to 90%. So this is R squared for linear fit.